Yeah, I've been told to stand here.
Dipan. And in Michigan and San Diego.
Yeah. Yeah. All right. Okay. Yeah. All right. Maybe I should start. Is this on?
It's all right.
Okay. All right. So thank you, and thank you for having me here. So this visit of mine actually comes through a small grant that I have with Ranjan, which sort of materialized a seed funding arrangement with Ranjan and Sudhir and Yvonne in Sydney. So Yvonne was here. As a small grant with which we had an opportunity to have an exchange of students, etc. So we've been talking to each other for a while, and so this comes at an opportune moment. So Ranjan and Adarsh will probably visit us sometime in March. So when I had a chat with both of them and I was wondering what to talk about, I was told not to talk about, well, it was suggested that I should not talk about dark matter because we've had a lot of those, and so I thought I might as well say something that talk about something that we've been working on for a while. But this also has a dark matter story to begin with, although so the bulk of the talk, and almost 90% of this talk, will not be about dark matter, but will be about scattering amplitudes really. This started and has a lot of protagonists and a lot of hardworking students. So I should mention this person, Dennis Forden, who was a student with us in San Diego, who did a lot of heavy lifting, and because this involved a significant amount of hard calculation, and has moved on since then after his PhD, and works at Wolfram, where he manages the entire integration routine package of Wolfram. So that's one way in which learning Mathematica can actually give you a high-paying job, and he actually heads that department now. So if you want to talk about Monte Carlo integrators, contour integrators, doing machine learning with integrators, etc., that's the person you want to talk to. Then I had two wonderful students. This person has now moved on from his master's to do a PhD with me and Sekhar. Jing, who was a postdoc with us, is now a postdoc with Roberto Contino at INF in Rome. And so I'll talk about, this will be a sort of a hybrid talk, so I'll not go full theory, I'll not go full pheno. So at any point, if any of you are unsatisfied with my, explanations or about my approach, it's just because I really want to take a sort of middle path, and so none of you will probably be entirely satisfied. All right, so this visit also comes at a time when Rohini is not here, and Rohini was one of my first entry points into IISc. So and as young graduate students, both me and Kirtiman were indebted to her for a lot of support. And as well as, whenever we went out, whenever we came back, we always saw her. And so it's absolutely heartbreaking for me to not see her around here. So one of my first memories of Rohini was, of course, when Kirtiman came to TIFR and we started working on something together. And since then, we've had a lot of exchanges. I wrote a bunch of papers with her. And one of my first memories with her was when the two of them, when she and Fauzi played a prank on me. So this is in Les Houches, where they caught me sleeping during a lunch break in the bar. So this is the bar of Les Houches, if you have actually been there. And this showed up in the yearbook of Les Houches of that year, and was shown in the summary talks in 2013 in Les Houches when I was still a graduate student. All right, so she was, she was really someone who I have missed over the last year, have thought about a lot. All right, so let's start this talk. And so the prologue to this is something that we started thinking about in 2017 or 2016, actually 2017, when we were looking at Randall-Sundrum models, and we were looking at something related to phase transitions and dark matter physics. And naively, what we wanted to do was, at the first place, estimate a bunch of cross sections, and that was as simple as that. But this is Randall-Sundrum model. These are extra dimensions. People had worked on these for a long time. So although we knew parametrically what we should expect out of a simple calculation, we wanted some numerics. And well, so the type of papers that we saw in the literature at that time. So this is a cartoon of a 5-dimensional world where you have some hidden brain, which is normally called the Planck brain, and we sit in this TV brain, which is where you localize some standard model fields and some potentially some dark matter particle. And then the physics was that, well, you can saturate the relic density by interacting by annihilating the dark sector into the standard model sector through this KK portal. So it's essentially just coming from gravitational interactions from the dark matter. From the dark matter interaction comes exclusively via gravitational interactions. So there's a lot of literature, and we thought that, well, okay, so this is a solved problem. At least we can get a parametric answer. To our amazement and to our confusion, we saw this. There's a whole lot of literature here, some appearing in PRL, and the problem here is that all of these claimed that if you just do a 2-to-2 scattering of 2 gravitons going into 2 gravitons with a massive spin 2 particle or massive spin 2 KK mode, the amplitude should scale like e to the 12. If you had matter couplings, if you had purely self interactions, this would go even faster. This would grow even faster. And what's crazy about this is, naively, if you think about this, if this m is the mass of a KK particle, as you take this limit m going to 0, this amplitude is going to blow up, and that's a problem. That's a problem for us. This was not a problem for the Pheno papers, and the reason is that if you have an amplitude that's blowing up, you can actually saturate the relic with relatively low KK scale. And it's a problem because, naively, if you think about, and as I'll talk about in this talk, the bulk of this talk, is that this scaling is everything, is not something that's consistent with the symmetries of the theory. And I'll go into detail about what this.
M is the KK scale which you're treating as sort of the mass of the graviton.
Yes. So I mean, think of this as a KK mass.
What you're seeing is basically kind of like a VDDC discontinuation.
Correct. So I'll come back to that. Correct. Absolutely
So
correct.
that's a natural solution for that in kind of,
Correct. Let's come back to that. Okay. That's the story. All right. So what should I expect? So this is sort of telling you that the scale. So I should really expect, because there is a higher dimensional diffeomorphism invariance, I should expect the lower dimensional, the EFT, not to exceed something like s over m Planck square. So if I really had something like this, this would suggest that the scale of the EFT scale of this theory would break down at a scale much below m Planck or whatever the emergent scale is if you're looking at an ADS curvature or something. So the idea is that the issue, this issue that breaks down in the so-called, that looks like something like a massive gravity, should be restored in a full Kaluza-Klein theory. All right, so I'll go slow, at least for people who are experienced in this topic. Probably this a lot of it will be repetition, but I'll go slow anyway. So why should I care about EFTs? Well, for the first part, at least if I write down an action at some d dimensions, so that Lagrangian would have a mass dimension d, and I can formally expand this Lagrangian as some Wilson coefficient times some operator. And for at least the lowest parts of that, there are kinetic terms for phis and psis if you have fermions and scalars. And once I know the basis, I can literally expand this as an operator of dimension d, which would, if you're in 4 dimensions, would start at some renormalizable piece and some expansion in operators of lambda. And a typical scattering amplitude with some momentum scale would simply scale like p by lambda to the d minus d. All right. So this exactly, this how things work. And the classic example is a 4 fermion theory, where you know that, of course, if you had if you were sitting at a scale much below the W, you would have a 4 Fermi interaction. The amplitude of that would simply, at leading order, scale like some Wilson coefficient times some current. And it's only when you start probing higher orders, when Q squared approaches MW, you would say that, oh well, this theory has sort of failed, and well, I need to think about the electroweak theory or something like that. Of course, you also know how this works in standard model. You have W bosons, the self-scattering of W bosons. If you have a massive W, the longitudinal W boson will start growing. That's because the longitudinal parts of the polarization would go like m k over m, and therefore the EFT would break down at some scale. And you know how this is resolved in electroweak standard model, that is the Higgs kicks in and unitarizes this amplitude. So we'll come back to this as well in great gory detail. All right, so sorry, no, I'm sorry.
This picture is basically, yeah, okay, so that's the standard.
Yeah, this is, so we'll come back to this. We'll come back to this in detail because this is something that I'll keep using. All right, so we can actually, we don't need to even think about the standard model. Let's start with something very simple. So let's start with something that looks like a massive photon. So let's start with a massless photon, and you know how to count the degrees of freedom. So a massless photon in 4 dimensions has 4 degrees of freedom. One of that is just a redundancy. It's called what you call the gauge freedom or gauge invariance. I don't like that word, but anyway, it doesn't matter. And the other one is just a pure Lagrange multiplier, right? So in d dimensions, a massless gauge boson has some d minus 2 number of degrees of freedom. If you add a mass term, that mass term explicitly breaks that gauge redundancy. And the way to sort of restore it, if you like that language, is to do a simple Stuckelberg trick. So you shift this a mu by an a mu plus del mu phi, where phi is some longitudinal mode. So there are 2 degrees of freedom in a mu and 1 in this longitudinal mode phi, which couples derivatively, right? And you can simply plug this back in as a proxy and expand this Lagrangian out. This Lagrangian, of course, now has a symmetry. That symmetry is simply the fact that a mu and phi are now gauge dependent on each other with this parameter lambda. But what's also important, once you look at this carefully, is that this longitudinal mode, which broke the gauge invariance, couples to the conserved current del mu j mu. Which also means that if you were to just look at the amplitude of 2 particles connected by a massless photon versus a massive photon, the m going to 0 limit is actually regular, and that just means, and that's just because of the fact that this longitudinal piece couples to a conserved current. So at this level, at this linear level, you can never actually distinguish a massless photon from a massive photon. All right. So formally, of course, you know that there is a abelian Higgs mechanism. That abelian Higgs mechanism actually generates a mass for the photon. Let's do this for gravity, and we'll see some surprises. So the classical action, as you know, is given by Einstein's equations. Einstein's equation is just the left hand side that's related to the Ricci and the Riemann. And the right hand side is just some source term, and for the time being I'll just consider use the fact that this source term is conserved. So of course the Ricci is a 2 derivative object at the kinetic level. Yeah. At least at this linear level, just because the longitudinal mode never excites. There's no kinetic. This is just a photon. There's nothing else. There's no this is not a dark photon. This is just Proca. This is just a Proca photon with a mass term. If the mass is arbitrarily small, you simply cannot distinguish it. Just because if you look at the amplitude between a massless and massive, the m going to 0 limit is smooth. Really high mass, obviously. Yeah, that's a different story. Yeah. All right. So I'll consider, at least for the time being, that the source is conserved. And when you know how to write down the polarizations, so how many degrees of freedom does this have? Well, naively, if you just look at the fluctuation beyond some classical Minkowski background, this is a 2-index object, so it's a matrix. It has 16 components. This is symmetric, so that takes 6 out, and then you have 2d degrees of gauge redundancies, so that reduces down to 2, right? So and you can write those 2 polarizations as just a direct product of 2 polarizations of spin 1 particles. And you can actually go ahead and do this calculation. This is a nasty calculation, but you know just by dimension analysis, what you should expect out of this theory. There's only one scale in this theory, and that's M Planck. It's a 2 derivative object, so there are 2 derivatives, therefore it should just scale like S, and that's consistent with semi-classical gravity. And once you know this, you can actually formally expand it in a power series of R. Well, let's also look at what the symmetries of this theory are. So there's diffeomorphism, that's equivalent to what you would call a gauge invariance. That's just shifting h mu nu by some arbitrary gauge parameter. and that's just h mu going to h mu plus del mu zeta nu symmetrized.
So the e to the 12 that you showed was for the square of that.
The square of the amplitude. All right. So let's count the degrees of freedom again. So that's an important thing to remember, and we'll come back to this part over and over again. So if you look at a graviton in d dimensions, so a d-dimensional graviton has d times d plus 1 by 2 number of total degrees of freedom, out of which you take 2d, and you're left with just d times d minus 3 by 2. That has consequences. It just means that in 3 dimensions you don't have gravitational waves. It's just non-dynamic. That's just a fact of nature. In d equals to 4, it just matches the total number of degrees of freedom that a photon has, and in 5 dimensions it has 5 transverse degrees of freedom, no longitudinal, just transverse. And compare that to the number of degrees of freedom in master stage boson. All right, let's add a mass term to this. So let's think of a massive graviton, and this is what is traditionally called the Fiat-Pauli theory. This mass, so it has two terms because it's quadratic, it has two indices, so I can literally write down two pieces to this. There's an h mu nu piece, a square of that, and a trace piece, which is h square. This sign is important, and this sign is important because I could have naively set up a system where I could have written a plus a b, and I could have left these free, but this is constrained. It's constrained by something called the Ostrogradsky theorem, and that's just a statement that you don't want to propagate more than 2 time derivatives when you write down the equations of motion. Otherwise you just propagate a ghost or a kinetic term with negative sign. Well, I can actually then play the same trick as a Stuckelberg. I can shift this, I can introduce some number of degrees of freedom in A, but this is 5, so I've broken the diffeomorphism in weights explicitly by a mass, so that gives you 3 additional degrees of freedom, 3 longitudinal polarizations. 2 of those are in A mu and 1 in this longitudinal degree of freedom phi, so there are now 5 propagating degrees of freedom, 2 in transverse and 3 in longitudinal, right? I can then write down this action once I plug these back in. I can rescale these A mu such that I have a canonical action. That canonical action would have an usual m equal to 0 piece, the usual Einstein-Hilbert piece, a piece that just looks like an f square, that's just coming from this part, a piece that just looks like a kinetic part for del mu phi, and a term that couples with the external stress energy tensor T mu nu. But what's important is that even after I assume that the source is conserved, that is del mu T mu nu goes to 0, this object, this phi, now couples to the trace of the energy momentum tensor. So the longitudinal mode now couples to the trace of the energy momentum tensor, and therefore just does not decouple from the theory. Because it does not decouple from the theory, it actually appears explicitly when you do an amplitude calculation. So the scalar roughly couples the trace of the energy momentum tensor, and it behaves like what's traditionally called a scalar tensor or a Brans-decay theory. It affects the Newtonian potential, it affects velocities of light, it gives you a cutoff, etc., etc. And traditionally, this is what is known as the Van Dam-Veltman-Sakharov discontinuity. And the idea is that the m going to 0 limit is not smooth under the Stuckelberg transformation. And it shows up in a variety of ways, and this is one way it shows up. The other way it shows up, so d equal to 2 it doesn't matter because, as I said, anything below 4 gravity is not dynamic anyway. A d equal to 2, so you can't, one-dimensional gravity, but you don't have any propagating modes anyway to start with. So there's a discontinuity anything anywhere below d equal to 4. That's a good point. In principle, yes, but I don't know what to think of that theory. In principle, yes, but I don't know how to deal with, like, I don't know what is meant by a propagating, like a massive graviton in 2 dimensions that has one like, I don't know what to think of that theory. But yeah, so that's one part. The Ricci would be exactly 0. All right, so so that's one way of thinking about this. The other way of thinking about how this VDVZ discontinuity shows up is if you just did a calculation where you just did a 2-to-2 self scattering of gravitons where the external legs are all massive. And the way this shows up is that if you write down all the polarization tensors, you'll see that the longitudinal mode comes with a piece which looks like E by m. So now you can just simply do the power counting. So this is epsilon mu nu of 0, so you have 2 powers of momentum over mass square. You calculate, so this is just the normal in massless gravity, this would be the diffeomorphism invariant set. So you would just naively calculate this, and you can actually do the power counting piece by piece. So every external polarization will grow like S over m square, the vertex will grow like S, and the propagator, which would naively grow like 1 over S square, but there is a hidden symmetry that would just let it eventually grow like 1 over S, and that would mean that the amplitude, if you just do the power counting, would grow like S to the 5 divided by mh times m Planck square, and again you see this discontinuity showing up. This is a discontinuity as n goes to 0, it does not reduce to the Einstein-Hilbert action. So this is another way of stating the same thing, that there is a discontinuity in the action, and this is what is the source of what's called the Van Dam-Veltman-Zakharov discontinuity, which also means that because this grows like S to the 5, these are what are traditionally known as lambda 5 theories, or that by that I mean that unitarity is violated parametrically at a scale much lower than, it's called a lambda 5 theory. So there are lambda 5, so it really depends on what power you go with. All right. So that's the idea, that unitarity is really violated at a scale much parametrically below Planck mass, and which means you expect, at least in this, if this theory was right, you would have expected quantum gravity effects to show up at that scale. All right. So one of the issues that people had been thinking about since the late 70s, and this is going back to the time of Van Dam, Veltman, and Zakharov. Yeah. So good. So let's break that down, right? So that's a good point. You see that this is really the longitudinal polarization, right? So in WW scattering, the longitudinal polarization would have told you that the amplitude would have scaled like S over mw square or something like that. That would be the leading behavior of that theory. So on top of that, so this is the highest power. So this, once you expand this matrix element in powers of S, this would be the highest power. Then there will be a piece that looks like S to the 4, S cubed, S square, etc. So this is so the transverse piece is just that. No, that's just because it's there are no E by M pieces there. It's basically the longitudinal mode. So the longitudinal modes come in 3 pieces. One is pure spin 0, and then there's a mixed piece which couples the two. So from the late 1960s or something, so people had been thinking about this, and the reason why they've been thinking about this is because, well, in all gauge theories, we know there is a Higgs mechanism. I know how to Higgs the photon. I know how to Higgs essentially the electroweak theory. So naively, gravity is a gauge theory, so I should be able to do this. There should not be an impediment to doing this. But every time people try to do something, there was a roadblock, and that roadblock stopped here at S to the 5, right? So one needed to diagnose what happens to this theory. So there was almost no or zero development in this thing, and there was a reason. Of course, we know in nature that at least the nature is consistent with a zero mass graviton. But tomorrow, if you did see a horizon scale mass for the graviton, at least consistent with what today's data tells you, which is that the graviton has a constraint on the mass that's about 10 to the minus 22 electron volt per c square. It comes from gravitational wave experiments. You need to find a way to figure out what that Higgs mechanism looks like. Otherwise, this theory is all inconsistent, at least in a semi-classical or a classical way. So there had been developments about if there is really a no-go theorem to actually giving the Higgs giving the graviton a mass in a classical sense, or even whether you can actually raise this cutoff. So if this cutoff goes from S to the 5 up to S, you're fine, right? If the cutoff starts slowly moving from S to the 5 to S cubed and onwards, you are in the right place. All right, so let's look at what's called nonlinear massive gravity, and this is the idea that, well, there is a square root GR, but the mass term is the lowest term in the potential. It's just a quadratic piece in this potential. I can, yeah.
Dealing with this thing is order S because it is gravity. If it is, for instance, a Higgs, it is a constant.
If you had a Higgs mechanism, it would be constant. Yes. All right. So the most general potential that you can actually write down. So the lowest part of this is the Fierz-Pauli term. That's just the h square minus h square term. But then you could have written down a series of nonlinear terms, which would have started with h cubed. So you would have contracted all possible ways of writing down an h cube, a Lorentz invariant h cube term with some arbitrary coefficients. You could have written something like a v4, v5, and you could have just continued doing the series. And the way to tune these coefficients is always, you have to remember that any such tuning, when you write down the equations of motion, should not generate ghosts, should not generate arbitrary kinetic terms with negative signs and things like that. So you have to keep tuning this, and this tuning is possible, right? So you can actually find a neat way of tuning this. This is what is called the tuning of these parameters to raise the scale, and you find that if you tune it in a particular way, this scale, which started growing like s to the 5, can be reduced down to s cubed by just this nonlinear tuning. This has a name. This sort of revolutionized the field of massive gravity. This goes by the name of DRGT, or the Diran-Gabbadar-Zettoli model. This is from 2010. This has been, since then, has been sort of, and this had sort of a phenomenological implication. The claim was that the DRGT gravity or bigravity or things like this would have given you a temporary solution to the cosmological constant problem driven by dark energy or what have you. So bigravity is one such theory where you have one massless and one massive mode. The massless mode with some assumptions would just look like something that looks like a Einstein gravity. The massive mode would have a cutoff, of course, but you can go to what is called a GR limit and play around and do a lot of with it. Since then, there has been a lot of development in this field about just bootstrapping amplitudes to see if there is really an impediment to raising the scale. So again, what I mean by raising the scale, I mean that if you could go from s cubed to s, it would mean that there is, although you don't know what the Higgs mechanism is, there would be a Higgs mechanism that would scale the s to the 5 right down to s over m Planck square, and that would mean that there is a genuine possibility that there is a Higgs mechanism that's going on. As far as we know, then no, it would grow like s in gravity.
This is what you get in pure gravity, but we know that pure gravity is anyway problem.
No, so what I mean by that is that if you wanted to treat gravity as an effective theory up to m Planck square, it should just scale like s over m Planck square. And what I mean by a Higgs mechanism is that mechanism, so this s to the 5, from s to the 5 to usual gravity, which would mean that in the sense of when you do a Higgs mechanism, you don't necessarily start from writing down the Higgs potential, right? You would have written down the nonlinear sigma model. That nonlinear sigma model would have told you that eventually there would be a Higgs mechanism of a certain type. So in that sense, you would have said that, okay, this is the structure of this.
It solves the problem that the extra stuff creates, but it doesn't solve the problem of gravity.
Yeah, in some sense, yes. So the point is that, so this raises the cutoff from lambda 5 to lambda 3. So by lambda 3, I mean that you can cancel off by just keep following this procedure. You can cancel off the s to the 5 and the s to the 4 pieces, but you cannot go beyond s cubed. So the cutoff right now, as far as the state of the art is concerned, is lambda 3. So which means that even with additional nonlinear pieces to this potential, the amplitude will grow like s cubed by m to the 4 times m Planck square. All right. So people have been looking at bootstrapping amplitudes to figure out what is it that is actually stopping it. And I'll say something a bit more profound about this. Maybe I don't know if it's profound, but I'll say something. If you want to go follow that literature, there's a beautiful paper by Cliff Chung and Grant Remen that looks at some of these issues about if there is a real no-go theorem to actually Higgsing the gravity sector. At tree level, this is all pure tree level calculation. This is again just imposing Ostrogradski theorem. So the reason is that some of these terms filter down here because you want to impose Ostrogradski theorem, right? And so the point is that anything, so you would get, so if you actually do the calculation, you'll see that there would be a circle in a dimension, in a dimension where you have a certain number of constraints in the c direction and a certain number of constraints in the d direction, but you can't really disentangle the two. So there will be a Venn diagram of c's and d's, though that would relate them to the two to each other. At linearized order. So it's not like h cube contributes to h to the 4. That's what I'm saying. It's not just a contribution in that sense. It's just that if you want to avoid ghosts in one direction in the C plane, it filters, so it's not a one-dimensional constraint. That's all. All right. So as I said, there's realizations of this setup. All right. So what should I expect in a compactified 5D theory? Well, so the compactified 5D theory, so the action is of course square root g times R5. So this has a 5-dimensional diffeomorphism invariance. So it has a 5-dimensional diffeomorphism invariance with a 5-dimensional Planck mass. And compactification should not, so even if I compactify, there will be an effective 4-dimensional theory, and that should not change the high energy UV behavior. And which means that the high energy behavior, if I was just looking at a compactified theory over a torus, it should just look like S over m Planck square. If I did a couple channel analysis, which means I took all n possible modes of these KK pieces, that couple channel analysis should just, by just simple dimensional analysis, I'll come back to that question immediately. Wait for it. That's the next subject that I'll come on. So if I do this couple channel analysis just by pure dimension analysis, it should scale like s to the 3/2 by m5 cubed. And so that's what we wanted to look at. So examine the strong coupling scale, and we'll do this just over a compactified torus or in Randall-Sundrum models, which are on ADS. So it just means that if you just looked at a 2 to 2 KK graviton scattering and you just looked at the 4D level, it should look like S over m Planck square. But that's not the story, because your high dimensional invariance told you that if you were looking at the full theory, it should look like S to the 3/2, which means it's not enough for you to just look at the 2 to 2. You have to look at all n possible graviton modes, sum them up, and then diagonalize it in that basis. So that would give you a root n. So those root n's would look like root s's. That would give you an additional factor of root s over m5, and that would just generate S to the 3/2. All right. So I'll take you back to 2001, and this is a paper that some of you may know. This is the deconstruction. So what do we mean by deconstruction? Well, you just discretize the dimension. So think of a 5D a lattice with near neighbor interactions, and think of these as near neighbor interactions like Ising model, where you have sites and links. You break a link, you generate a bunch of goldstones, which you can replace by Stuckelbergs, and then you can show that even if you took the n going to infinity limit with the lattice size going to 0, you actually never formally recover the full 5D. This theory also breaks down at lambda 5, and you can actually diagnose this problem where it comes from. In a full KK theory, you just don't you need all the interactions and not just the near neighbor ones. All right, so this is a famous paper by Arkani, Hamed, Georgi, and Schwartz. This is a paper that a lot of you are familiar with. So that's something to remember. All right, so let's do this for gauge theories in arbitrary dimensions. So lessons from gauge theory. All right, so let's remind you again of the Salam Weinberg Glashow theory. So as I said, that if you just looked at a WW scattering in unitary gauge, so you would naively calculate these longitudinal massive W bosons with longitudinal polarizations. You have 3 diagrams. Each of these would actually grow like e to the 4 by mw to the 4 because of the 2 longitudinal pieces. And then once you add them up, you actually see that the e to the 4 goes away, and that's just because there's a Yang-Mills structure, there's a Jacobi identity that just kills these off, and you're left with actually the e square piece, not just the e to the 4 piece. But the e square piece is also something that you don't expect, and this is where the Higgs kicks in. So the Higgs kicks in, it adds these 2 diagrams, you look at these, and then you sum them to 0. So the way to think about this is sort of a sum rule. The sum rule just relates a bunch of diagrams with bad high energy behavior to the pieces that actually unitarize the diagram eventually. If you were doing this calculation in a pure 'T Feynman on an RSI gauge, you would have actually never seen this divergence. You would have seen that the amplitudes, by Goldstone's equivalence theorem, you would have seen that the amplitudes would have grown like a constant from the outset. You did not need to do any of this. This is a pure artifact of the fact that we are doing this calculation in unitary gauge.
The Feynman gauge is basically possible because of the gauge.
The Feynman gauge is because I would have fictitiously added the Higgs as a sigma model. I would have then imposed the Feynman gauge. I would have imposed the gauge invariance, and I would have seen
Feynman
that.
Gauge is the one where the gauge fixing term basically goes to 0, right?
So I would have written a generalized R psi gauge, and then the psi will go to is going to infinity. And we'll come back to this again. All right. So if I can do this for Weinberg-Glashow theory, I can do this for higher dimensional models. So let's start with a Yang-Mills theory in 5 dimension. So all I'm doing is I'm taking a 5-dimensional theory and compactifying it over a radius of r. And I know what to do this. This is like a quantum mechanics problem. It's just take a particle, have it go around a circle, and just Fourier transform it, right? So I can write down modes of this equation. So there will be a 0 mode of this, that would be the lowest lying eigenvalue, and a tower of states, just like you do an eigenvalue problem. But not only that, these pieces, the A5s, are in unitary gauge, they would be eaten. In a non-unitary gauge or an RSI or a Feynman gauge, these would appear as gauge redundancies, or these would actually be eaten, the eaten Goldstone modes, such that I can relate the longitudinal polarizations per mode to this A5 piece. All right. So then this in this gauge, the kinetic terms will have some number of masses, some number of eigenvalues. So you'll see a set of massive gauge bosons, each with a mass mn. Then you'll see a mixing term that mixes this A5 piece and APU piece, and a kinetic term, a pure gauge kinetic term for the A5 piece. And I can do the same calculation. If I were doing this calculation in unitary gauge, you would have seen exactly the same behavior as the Weinberg-Salam-Glashow theory. I would have said, well, this scattering goes through, this is in flat 4 dimensions, so there's momentum conservation. So if I had a mode number n and a mode number n going to a mode number n, it would go through a 0 mode and a 2 mode. And then if I add all of these, you would see that all of these modes simply cancel out, and naively these longitudinal modes that would have carried an s over mw squared would just simply cancel out. And this is purely this cancellation, that the idea that you see this cancellation in unitary gauge is again an artifact of the fact that I have replaced all of those Goldstones with the masses of these equal modes. All right. So the generalizations of course is that this is not just true for an for just a flat manifold. You can do this in ADS or what have you, and you would see that the kk eigenvalues, the eigenvalues of these kk modes and wave functions, they depend on boundary conditions, they depend on the overlap, and you would see that this is a Lorentz invariant piece and all of that. So I'll come back to this point. What you would also see is that this system of kk gauge theory also implicitly has a deeper structure. It hides something called two copies of n equals to 2 supersymmetry. So you could reformulate this entirely in terms of supersymmetric quantum mechanics language, and you would see how the cancellations occur. And I'll again come back to this problem in a bit. All right. So that's the story of the gauge theory. The story is that the 5-dimensional Yang-Mills theory is unitary. You can either go to a unitary gauge or a 't Hooft-Feynman gauge. In the 't Hooft-Feynman gauge, you never actually see the cancellations. All you see is the amplitude is regular from the start. If you were in unitary gauge, you would see explicit cancellations, and you have to really be careful about how you're calculating this. You have to keep track of all the 1 by square root 2's, all the masses, and then relate all of this problem to an eigenvalue equation. But at the end of the day, even in 't Hooft-Feynman gauge, you would, or in unitary gauge, you would see this amplitude being regular, which means that the amplitude scales as you expect, with some dimensionful scale coming from the 5th dimension.
So the reason why that's not possible is because it's basically not normalized, not renormalized. Right?
The higher dimensional.
We start with the 5D Yang-Mills.
Yeah, so the 5D Yang-Mills has a scale, right? That's M5. So this amplitude would just scale like order E. Or not order E, a constant. Just a constant, nothing else. At lower dimension, at the 4D level. Yeah.
So because
but otherwise at 5D level, you would just get the dimensionality, the scattering amplitude, some dimensionality of that scale. All right. So let's again move and take this lesson and go to interacting spin 2 theories. Well, so you know what to do. It's the same procedure. You write an action. So that action has a square root g times an R4 and an R5 piece. And well, so if you wanted a low energy effective theory, you would just integrate over the extra dimension. So this is just an orbifolded torus, which just means that I am identifying the even parts of this this geometry. And that just means that all these h mu 5s, the odd parts of this, will just vanish under orbifold. I can integrate this extra dimension and I'll get a 4D theory with a cutoff. I can also, which just means that, well, that a 5D theory, so that's the ansatz, well, that's the input and output. A 5D theory will just appear as a tower of Kaluza-Klein modes. from a 4D point of view. There's a mode equation with the profile in extra dimensions. Those will be obtained by just solving an eigenvalue problem. So that eigenvalue problem will just look like a Schrodinger equation or a Sturm-Liouville problem, if you like, with some wave equations in 5D. And the coupling of these particles will just be proportional to the overlap of these integrals, right? So that's your 5-dimensional manifold. There's a 4x4 block. These pieces will just get vanish upon orbifolding. The higher modes, of course, as we see, get Higgs. And then there is a 5-5 piece, which is what we traditionally call the radion or the dilaton. That's just the broken scale invariance, because I put explicitly a boundary across the geometry. So that's just what you traditionally call the dilaton. I can also do this in ADS. So I can look at something that looks like a Randall-Sundrum model. So where I have a Planck brane and a TeV brane, and all that's happening in this is that my bulk geometry is anti-de Sitter. So it just means that my effective scale just scales down from some higher Bev to some TeV scale object that resolves the hierarchy problem. And at least for this talk, what we'll do is to parameterize the metric in the so-called Einstein frame, and that just means that I'm writing out this metric in a way such that my quadratic kinetic action is diagonal. If I wrote it in some other way, I have to do some random field, some arbitrary field shifts, etc., be consistent with boundary conditions. That would be a mess. Instead, we start with a frame where my quadratic canonical piece of the Ricci is diagonal. The good thing about this model was, of course, when it was first proposed, and then you had TeV scale masses that would have resolved the electroweak hierarchy problem. The Higgs wave would have scaled down from some Planck scale to some low energy scale, and that was the original motivation. For us, what we want to know is what is the effective, if I did a 2-to-2 scattering of kk gravitons, what's the effective scale of this field? So my prescription is simple. I take a 5-dimensional model, I integrate over the extra dimension, and I get something that looks like a effective 4-dimensional action. So I would just expand this in a Fourier series. I would get a spectrum that's orthonormal and complete with a discrete set of states that would take a 5D graviton and spit out a 4D graviton plus a massive spin 2 tower. It will describe a Hilbert space of wave functions, which would be satisfied by a Schrodinger equation, which has orthonormality, it has completeness, it forms a complete set of states, and that's just a basic fact, and that would be true even if you took a particle that went around a circle. So if you had the solutions to this, at least in the unstabilized model, is that if you have a torus, it would just look like a cos. If you have an ADS, it would look like some complicated Bessel functions. All right. So we want to look at amplitudes. So let's do this calculation. So this generates about 100,000 Feynman diagrams, which is what our student did in Mathematica. He managed to integrate this amplitude effectively, put it into a package, and it's now available to us, where you can actually expand the Ricci in any arbitrary background to any order in perturbation theory and just do at least at tree level we can do this calculation. All right, so this itself, the KK exchange diagram produces about 78,000 diagrams. The radion exchange diagram produces about 20,000. The contact piece produces about 25,000 diagrams once you symmetrize over all indices, once you take all permutation symmetries into account. And this is the artifact of doing this calculation in unitary gauge. It simply keeps blowing up. All right. So how does this behave? This contact interaction, if you just did a kk to kk calculation, this amplitude grows like s to the 5. If you did a kk exchange, this amplitude naively grows like s to the 5. If you did a radion exchange, this amplitude naively grows like s cubed. Great point. Absolutely. Let's come back to that as well. Right? It simplifies. If you use spinor helicity, it simplifies if you use double copy, it simplifies if you use a certain type of different techniques as well. So we'll come back to that. All right. Okay, so we were of course naive when we first started this calculation. So we did absolute brute force, like no simplifications, no assumptions, no fancy tricks, nothing, just brute force, 100,000 diagram calculations. All right, so how does this calculation shape up? So you want to calculate all of this. So the way you do this is that all of these 4 and so the tensor structure of this is just determined by the underlying tensor structure of the Ricci, and the couplings are just overlaps of these wave functions. All right, so you have 3 or 4 types. But because this is a Ricci that you're compactifying down to 4 dimensions, so you have derivatives in the 4 direction and the 5 direction. 2 of those derivatives actually turn up as del y square, so you can neatly separate this out into a 4-dimensional part and a 5-dimensional part, and these are what we call A and B type couplings. So A type couplings have no derivatives coming from the 5D part, and the 4D part has 2 y derivatives. The 5D pieces have 2 y derivatives. So these are, you can literally write down a Lagrangian where you can separate out these pieces. All right. Let's do this calculation again. So these are your polarizations. I want to calculate everything. So the way this shows up is quite unique. So at s to the, so you then take this whole matrix element and you expand this in a power series in S. So there's an angular part that's coming from this amplitude, and then there's just a series in S that starts at s to the 5. And the way it appears is exactly as you see in Salam-Weinberg-Glashow theory. It appears as a bunch of coupling relations which you can analytically prove actually just by using the properties of Schrodinger equation, and that just cancels off the s to the 5 and s to the 4 piece. At s cubed you want the radion, so there's another sum rule that you can again analytically prove. This cancels down, and you're just left with s over m Planck square or s over lambda square. That's the upshot of it. Now you of course don't want to do this calculation. I mean, this is a calculation that we did over 1.5 years, where we made an infinite number of mistakes. We knew it was of course wrong, because I mean, if you start seeing amplitudes growing at a certain rate, you know that it's wrong. So this is not something that is advisable to give to a graduate student. He enjoyed it, he got a job out of it, Mathematica was impressed, fine, you know. This is not something good. So we made this checker. Sorry. So the radion shows up, so it depends on, okay, let's go back. It's the spin 0, it's the dilaton. Yeah, so that's just the dilaton, just a spin 0, a scalar, master scalar. All right. So this is what happens. So this is 5 polarizations. So that's 625 combinations of amplitudes, which we drew in a checkerboard before we actually applied any of these sum rules. Once you apply these sum rules, all of them just unitarize it uniquely. If you actually look closer into this amplitude structure, you'll see neat patterns of how amplitudes or helicity combinations grow in a certain way. And again, as I said, this is not something that you want to give to a graduate student, but okay, fine. So you start doing the calculation. So there are 5 polarizations. So you have 2 incoming and 2 outgoing states. So that's 5 to the 4 combinations. So those are all 625. And each of these 625, so for example, if you look at this 10, this amplitude, so which is helicity 0 going to helicity 0, helicity 0, this amplitude goes like e to the 10. So this piece, which is a helicity, this is a helicity 0 and a helicity -1, sorry. This grows like e to the 7.
Oh, it is the power of,
it's the power of e, and then once you apply the sum rules, everything cancels down, and what you see is e squared or s. So this is, so lambda 1, we take lambda 1 and lambda 2, and then so you then blow this up, and each one has a corresponding lambda. Yeah. All right. So this is, as I said, this is a monstrous calculation, so we want to do something smarter. So let's actually not do this calculation, and we know by we know from our experience that if we really did this calculation properly in a Thorpe-Feynman gauge, I should not have to see this cancellation. I should be able to see an order as growth from the start. So let's do this calculation in Thorpe-Feynman gauge. So what we do is to rewrite this in conformal coordinates. So it has a bulk Einstein equation. In unitary gauge, naively would have set these to 0, but we keep these. And let's be smart. So let's decompose the system into what's called a quantum mechanical eigenvalue set. So what that means is that, as I said, once you compactify this, it generates a Schrodinger equation. That Schrodinger equation you can factorize. You can factorize into a d and a d daggered piece, and that gives you a set of eigenequations. That eigenequation happens to have a dual, so the d dagger d and the d dagger produces the same eigenvalue, which means that there is a mode, there's a degeneracy in this system. That degeneracy in the system enforces that all of the masses of of the KK expansions are absolutely the same. You can rewrite this in terms of an algebra, an algebraic equation in terms of two supercharges Q and Q dagger, which actually gives you a two interleaved quantum mechanical supersymmetric system. So we can use this to our benefit and reformulate this entire problem in terms of a Goldstone equivalence theorem. All right. So let's do that. So we write down a gauge fixing piece. It's just a feature of this of the Schrodinger equation. So the Schrodinger equation you generate, Sturm-Liouville equation, I should say. So you compactify theory down. Okay.
I think what you have is basically the Laplacian on this compact space.
Yeah.
Writing in a certain
yes. So yes. I am interpreting it as two supercharges, but that is important because it's an important revelation because what you realize is that this enforces that all of your there's a degeneracy in the system, and I can use that to my benefit. All right. So let's do this Thupf-Feynman gauge fixing. So in the Thupf-Feynman gauge, I can add a gauge fixing term, and I can neatly separate out, and we've actually used some of these SUSY techniques. So to actually separate out what's called the Lichnerowitz operator piece, which is the pure gravity kinetic part. There's a part which is a pure gauge degree of freedom, and a longitudinal part which is phi. So this is exactly what you would do in a Salam-Weinberg-Glashow theory. You would separate out the polarization degrees of freedom into a pure Goldstone piece, which would be these phi's and a's, and a pure transverse piece, which would be in this H. And as long as I can track the amplitude of these pieces, I never need to calculate these horrible graviton amplitudes. So all I need then is just the scalar amplitudes. All right. So that's the upshot. That's exactly what you do in standard model. So what matters to us is only the bosonic part of supersymmetric electron. So there is a supersymmetric, so there is a Ward identity which imposes that the longitudinal degrees, and let's come back to that there's a longitudinal degree of freedom that obeys a supersymmetric algebra, and that I can use to formulate a Ward identity where I can relate the Ward identity of Goldstones to the original amplitude. All right, so let's do that. So that gives me what's called the gravitational equivalence theorem, and that equivalence theorem is that if you have longitudinal polarizations in the KK spectrum, those longitudinal polarizations, just like the Salam-Weinberg theory, I can relate to the Goldstones of this theory. So I never need to calculate complicated Feynman diagrams of gravitons. I can simply go ahead and calculate the Goldstone amplitudes. And these Goldstone amplitudes will never grow as fast as s to the 5. They will grow from order s to start with. Just purely that. This calculation is a bit more hairy just because you need to keep track of all the Goldstones, but it's infinitely simpler than just brute force calculating a bunch of gravitational diagrams. All right. So that's the upshot. That again, if you were to do this calculation, going back to what people did in dark matter, you would just realize that power counting just shows that order amplitudes are order s. All right, and that the gauge invariant. Well, I will actually skip this. So, but we just to remind people that the RS system is not actually a good has a massless mode, which also behaves like a scalar tensor theory. So you need to stabilize this model. So you add a bulk potential and stabilize it. And naively, this introduces additional complications. So you generate an additional mode that screws up the scattering amplitude. But eventually, once you take everything into account, this is actually a fine system. So this is the first part of my conclusions. So how do these bad high energy behavior get tamed in extra dimensional models? So massive spin to particles just grow like s to the 5. However, once you take high dimensional diffeomorphism invariance, everything scales down to s over m Planck square. All right, you can actually stabilize this. This naively grows like m. Again, reintroduces the problem, but if you do this calculation carefully, you would realize that that's also not a problem. All right, so let's take this if I have some time. All right, so this is again a hairy calculation too. Anyway, I have told you one way in which you could have simplified this calculation. Let's think of another way you can simplify this calculation. So gauge theory amplitudes are infinitely easier to calculate compared to gravitational amplitudes, so I can use that. So what is a double copy? So let's do a short summary of what is meant by a double copy. So let's just take pure gluon scattering amplitudes. So there are three diagrams plus a contact piece. So if you just looked at this structure, you would realize that the tree level diagram you can just factorize into three S, an S, a T, and a U piece, and you can write them down in terms of some kinematic factor N times some color factor C over the S, the T, and the U pieces. The contact interaction, so there's a contact piece as well in this gauge invariant set, but you also know that there's gauge invariance, and therefore you can factorize the contact interaction into any of these additional pieces. Well, so that's something that we know, but I can use this. Gauge invariance, of course, demands that the amplitude must vanish under polarization momentum replacement, so I can simply do this, right? And then I can use, and you know that this process just means that there is what's called a color Jacobi identity and a kinematic Jacobi identity. These are all things that you know from your QCD class, right? So this is just NS plus NT plus NU. So that's just the statement that the Jacobi identity that you enforce at the color level, if you use on-shell conditions, it just gets related to a kinematic Jacobi identity. So that's something that you know from gluon amplitudes or Yang-Mills or just pure QCD amplitudes. Well, so what can we do? We realize that color and kinematic.
People know about the kinematic Jacobi identity.
Yeah, this has been known for a long time. Yeah.
It's like back before all this learned BCJ or whatever.
So BCJ used this fact. Yeah. I mean, but the kinematic Jacobi identity was known. So this is one form. This is what the double copy that I'll tell you is what's called traditionally called the BCJ double copy. There's also the KLT. Yeah. But the BCJ just use this at tree level. BCJ just use this. All right. So what can I do? Well,
BCJ and the KLD
yeah, they're both the same. Yeah.
Before the BCJ paper, did people consciously realize about the kinematic?
I think they are. So my understanding is that this was known. That the leap was here. The leap is here, where you simply realize that the color and kinematic factors are mutually interchangeable, which means that if you simply take the color pieces, replace it with the kinematic pieces, change this gauge theory amplitude into 1 over m Planck, what you get is simply a gravitational amplitude, and that's the statement of the BCJ. Just that you can just interchange color and kinematic identities. All right. So that just means that I can simply do polarization replacements. And this is the seed towards also doing a bunch of spinor helicity calculations. Well, what can I do with this? Well, I can use this, right? So I can write down a 5D Yang-Mills. Yeah.
No.
So this is just going back and imposing the kinematic Jacobi. So these are all mutually circular in statement. All right. So what can I do? I can write down the Yang-Mills theory in 5D. I know exactly what to do with this. I can write down the 3 polarizations. I can actually then do a gauge theory calculation of of the gauge amplitude in 5D, and I can then compactify it down. So I can start doing the 4D KK amplitude in 5D, compactify it down, do a bunch of on-shell conditions with 5D Yang-Mills, do a color kinematic reshuffling, and I would exactly get the gravitational amplitude in 4D. So I did not need to do any of this. 3 years of a student spent in calculating hundreds of thousands of computing time and Mathematica time. I could have just replaced it by this. This is of course true in flat space time. If you take ADS, this gets significantly more complicated. That's because the tensor structures still work out. The kinematic structures are much harder to get, and we still don't know the right prescription to do this. I think if you use spinor helicity techniques in a proper way, you may be able to do this, but I don't know how to. Well, we don't know yet how to actually go from in the ADS. In flat space time, this is absolutely crystal clear. Okay, so that's my end. So this is a slide that the flash. Most of this I don't know, of course. So this is from the slow mass theory study from Tim Adamo, where this is what is called the web of double copies, about where double copies have been used in the literature, in the whole phase space of this literature. All right. So and we are here essentially. Okay. So that's the end. So the last chapter. So I said that this no talk is ever over with without dark matter. So I don't know if any of you have seen this series. It's on Apple TV. It has nothing to do with dark matter, but it has everything to do with multiverses. So I invite you to go see this and well, laugh at it, ridicule it, whatever you want to do. I watched all of it, but anyway, uh, this is on Apple TV. It's a it's a thing to see. I mean, I would urge you to. What, have you seen this? There's a book as well. I think the book is, my opinion is that I've read the book after seeing the series. The book is infinitely better. All right, so I went back and said that the way we started this project was to look at dark matter and trying to correct a lot of these things. So we eventually corrected this, and we saw that where in these models dark matter is saturated, what the LHC exclusions look like, what the direct detection exclusion looks like. So that's the neutrino flow. This is where you would saturate dark matter through a KK portal, etc., etc. So that's my yeah. So lambda phi fixes the cutoff. The amplitude just grows like S over lambda square, and what you see. So I know the cross section. So this neutrino. Oh, for the lambda pi, because I can calculate exactly. So, and these pieces are just sitting on the KK resonances. So this is just a resonant enhanced KK scattering cross section, and the direct detection sits somewhere here. So yeah, that's here. So the dark matter is a variable on this axis, and this is the first KK mode, the first KK graviton. So as you vary, so every point that you see here is where the dark matter sits on resonance with the first KK. This is relic abundance by freeze out. Just freeze out. This is nothing else. Just okay. So think of this as replace the Higgs portal with a spin 2 graviton. So this would be a target for CTA. That this is exactly like it. Yeah, it's exactly like it. Yeah, so we fix this. So that's lambda. Yeah. All right, so the epilogue is here. So there's a huge number of threads from where we go. So there are things that I did not talk about, and the one thing that I did talk about, and this would actually require a theory talk, not a pheno talk, which is to look at what are called DGP models, or the Porati models. So these are traditionally what were called S-cube theories. I would sort of spend about 40 minutes to talk about some subtleties here and why we think that DGP models are oversold or were oversold at the time when it came out. There is a thread here that goes into amplitude behaviors in what are called swamplands or multi-brain setups. You could actually, as we've said, we've started retranslating all of this into a spinor helicity formalism. That's one. And then there is the bigger question about a connection with the so-called massive gravity community that's sort of driven by more of the Gabadadze, Tolly, Dirac community. Yeah, so the upshot is that that there's still a lot to do that connects pheno to theory, and it shows up when you try to do a serious calculation where people are sometimes naive. That's all I can say.
So the massive gravity thing, so when you have this potential of the rotor, is there a way to reverse engineer it?
Good. Yeah. So that's where you want to do actually a proper theory talk. So yes. So the point is the following. So write down. So this is what I would start with. So do a bootstrap. So what do I mean by a bootstrap? Write down all possible spin 2 Lorentz invariant terms, starting from kinetic pieces to all orders in perturbation theory with absolutely arbitrary coefficients. All right. And then ask yourself, when does this theory behave like a theory of massive gravity, and when does this theory look like a theory of extra dimensions? And you can explicitly show that the tensor structures force you. So the only way you could actually get down from S to the 5 to S is if your coupling structures actually matched exactly the coupling structures that were of extra dimensions. Anything else would give you a theory of S cubed.
If you did a similar calculation with a single massive, like for a spin This is for spin 2.
This is for
If
spin
spin
2.
0, you would have a finite curvature.
So exactly. So if you had a spin 0 or a spin 1, you would always see that there's always a Higgs mechanism at play. You could always relate those coefficients to a genuine Higgs mechanism, which is not the case. The only way this can happen is an extra dimension, which is a genuine Higgs mechanism. And so that's the bridge, right? That's the bridge that you want to build. That's the place where you want to ask yourself, is there a no-go theorem that actually is preventing you from taking that leap from S cube down to S, that connects the massive gravity? Because one of the reasons is that massive gravity, you don't have a pole, a zero pole, like you don't have an m equal to 0.
That's not a problem
Because of the so-called Weinstein mechanism. You say that, well, the Weinstein mechanism tells you that there's a finite screening cutoff of this theory where you should expect nonlinear effects to take into account everything of that kind. But that's not that's the old school way of thinking about this problem. The way you want to really think about this problem is that if you did a bootstrap and converted this into a unitarity and causality problem, is that telling you something about whether you can Higgs it or not? In the community, if you go and talk,
I didn't really follow what is because I thought that the idea was that what was the statement that you made about it coming definitively from the compact dimension?
so the compact dimensions is when you compactify a dimension down and you see that the amplitude is regular, that's because there's a genuine Higgs mechanism going on there, because you can relate the Goldstones to a lower dimension. So when you look at massive gravity, you've actually taken the m. So there's no m equal to 0 state there, right? So there's no pole in that piece. In here, the fact that you have a pole is one solution, but that's not the only problem, because you could have.
I think what you're saying in some sense is that these theories really are not massive gravity theories.
So extra dimensions are not really massive gravity theories, but it tells you that because the tensor structures are universal, right? If you did not know anything about the way gravity behaves for extra dimension, if I just give you a tensor h mu nu and asked you to write down all possible Lorentz invariant terms with arbitrary coefficients, you could have landed up in either of them depending on what your taste is. It's just that physically, I mean, we see Einstein's gravity, so that's Einstein's gravity.
Okay, so that's what